chapter, we're going to talk about capacitors. Now, a capacitor is an electrical device that stores energy. And a capacitor is basically made up of two conductors with an insulator between them. So it could either be two parallel plates or with air between them, or you could also have another insulator inserted between the plates. Or it could be a spherical capacitor where you have two spheres, one inside another, again the space separated by an insulator. Or it could be a cylindrical capacitor. So that's what we're going to look at in this chapter. So capacitors store electrical energy, and capacitors have many applications, just as some of the computer keyboards have capacitors. Defibrillators use capacitors. Radio and television tuning, we use capacitors. And motors have capacitors associated with them. So there are many applications of capacitors. The basic formula of capacitance is, it is the ratio of charge to the voltage. So Q is the charge given to the parallel plates, and V is the voltage between the plates. So this shows that if we could give a bigger charge, Q, and keep the voltage from being big, then the capacitance becomes bigger. That's obvious. If Q is big, yet the voltage is small, then the capacitance is big. We'll see how that is done as we get along. And then the unit of capacitance is farad. 1 farad is 1 coulomb divided by 1 volt. So farad is coulomb per volt. So here we see different types of capacitors. So this is the keyboard capacitor, and as this key is pressed down, as you can see that one plate is movable, so the plate moves, and that changes the distance between the two plates, and we will see that when the distance changes, the capacitance changes. And then you have other kinds of capacitors here, all kinds of capacitors, ceramic capacitor, you have an electrolytic capacitor, and so on. And if you look carefully, you can see that here the capacitance is in microfarad. See, so that's the usual thing, because a farad is a big unit of capacitance. It's like a mile. So we need inches. You see, we need smaller practical units like microfarad, which is 10 to the negative 6 farad, picofarad, which is 10 to the negative 12 farad, nanofarad from 9, which is 10 to the negative 9 farad. So now let us try to find the capacitance of a parallel plate capacitor. Deriving this formula is very important. Here we're going to use what we got from the previous chapter, that is Gauss's law. We're going to see that we've actually seen that the electric field between two plates is given by sigma by epsilon naught. E is sigma by epsilon naught. Now what is sigma? Sigma is the surface density of charge. Sigma is the charge on one of the plates divided by the area of the plate. So here you see the plates here. The plates have charges plus Q and minus Q. The red arrows represent the electric field from the positive to the negative plate. And sigma is once again the charge on one of the plates divided by the area of that plate. And the electric field between the plates is sigma by epsilon naught. And this is the case when we could consider that the distance between the plates is relatively small compared to the area, which is the case in a parallel plate capacitor. So once you get that formula for electric field, we should remember that electric field is also connected to the voltage between the plates by using this formula. E is equal to V by D. So d, little d, is the distance between the plates and V is the voltage. Now rearranging that, you get voltage is E times D. Now substitute for E as sigma by epsilon. So you get sigma by epsilon naught times D. Now substitute for sigma. Remember, sigma is Q by A. So we get this formula, and that is the formula for the voltage between the two plates. Now it's quite easy to find the capacitance because we know that capacitance is the ratio of the charge to the voltage. Therefore, writing C is equal to Q by the voltage and substituting for the voltage from here, we will get Q divided by, obviously this flips, epsilon naught A goes to the top, QD is in the denominator, the Q's cancel out, and then you get epsilon naught A by D. So that is the formula for capacitance of a parallel plate capacitor. Number one, notice that the capacitance does not depend on the charge. Mathematically, the charges got cancelled. Now, capacitance depends on epsilon naught, which is the permittivity of free space. So in this derivation, we are considering that the material between the plates is air. So epsilon naught is the permittivity of air. It has a value 8.85 times 10 to the negative 12. I'll write that. 8.85 times 10 to the negative 12. A is the area of the plates. D is the distance between them. So question is, how do you have an increased capacitance? Well, by increasing the area of the plates and decreasing the distance between the plates. Now there is a danger in decreasing the distance between the plates because one plate is positive, the other plate is negative. If you bring them very close, there will be an electrical discharge. In order to avoid that, we insert an insulator between the plates. Remember, air is already an insulator, but its insulation properties are not that high. But instead, if we could insert a piece of mica, you see that it insulates more. So now, not only are you avoiding the discharge between the plates, you are also increasing the capacitance. Because we will see as we go that now the new capacitance with mica becomes K epsilon naught A by D. There, you're going to insert a constant K, and K is called the dielectric constant. For mica, it's about 7. What does that mean? That means if instead of air, you have mica, then the capacitance of that capacitor has become 7 times more. Without changing the area or the distance between the plates, just by inserting a piece of mica, the capacitance has become 7 times more than what it would be with air as the dielectric. So we will go into details of that later on. Now here is an example that I'm working out, a simple one. Consider that the area of the plates is 1 meter squared. The distance between the plates is 1 millimeter, using 1 just for easy calculations. Now 1 millimeter, we got to change that into meter. And we find that, okay, that's the value of epsilon naught, permittivity of air. And then 1 millimeter is 10 to the negative 3 meters. So when we do these calculations, we are going to get 8.85 times 10 to the negative 9 farad. But 10 to the negative 9 farad is 1 nanofarad. So this capacitance is simply 8.85 nanofarad. Now remember, 1 meter squared is a huge area. So even if we had an area of 1 meter squared and kept it really close, like 1 millimeter, still the capacitance is only 8.85 nanofarads. So practically, capacitances are small. Although there are capacitors that have capacitance of like 1 or 2 farads used with air conditioners and bigger motors and so on, usually the capacitances are small, measured in nano, pico, and microfarad. Now let's talk about a spherical capacitor. In a spherical capacitor, you have two concentric spheres. That means the centers coincide. And it's separated by maybe air or a dielectric. As shown in this diagram, the outer sphere is given a negative charge, negative Q, and the inner sphere has a positive charge, plus Q, induced on it. So the radius of the outer sphere here is R2, while the radius of the inner sphere is R1. In order to find the capacitance, let's assume a Gaussian surface as shown here, a spherical Gaussian surface of radius little r. And when we apply Gauss's law, we know the closed surface integral of E dot dA is equal to 1 by epsilon naught times the charge within the surface. And if this is the Gaussian surface, the charge inside that surface is plus Q. So that's why on the right side we have Q by epsilon naught. And on the left side, when you look at the factors, we see that E is going to be a constant at all points. The electric field is a constant because it is at the same distance from the center. And so we got to do integral dA. When you do integral dA, you get the surface area of that sphere, of the Gaussian surface, which is 4 pi r squared. Therefore, E times 4 pi r squared is Q by epsilon naught. And when we rearrange the electric field, E is 1 by 4 pi epsilon naught Q by r squared. Right? We have seen this before, that the charge now behaves as if all the charge on the inner sphere was concentrated and situated at the center, because that's the field due to a point charge. Now, continuing, we know that the definition of voltage is integral R1 to R2 E dot dr. We know voltage is the integral of the dot product of E and dr. But E is 1 by 4 pi epsilon naught Q by r squared, which I have substituted. So we got to finish the integration. Everything here is a constant except 1 by r squared dr. And the integral of 1 by r squared dr is negative 1 by r, right? So when you do that, the constants are taken outside. And then you have integral dr by r squared, which you see is negative 1 by r. So I've not written the negative because actually I have reversed when I substituted the limits. It's supposed to be 1 by r2 minus 1 by r1, right? Upper limit minus lower. Instead, I've written it as 1 by r1 minus 1 by r2, thus avoiding the negative sign. Now, finally, we know capacitance is the ratio of charge to the voltage, and all we got to do is substitute the value of charge, which is Q, divided by this entire thing. Now, before dividing, I've taken the LCM here, which becomes R2 minus R1 divided by R1 times R2. Okay, but then it flips because it's in the denominator, and finally you end up with the capacitance of a spherical capacitor is 4 pi epsilon naught R1 R2 by R2 minus R1. So now the question is, how do we have an increased capacitance? Because our goal is to have an increased capacitance. Because that would mean an increased ability to store charges. All right, so how do you make that big? By making this factor small. So if you want to make R2 minus R1 small, then you got to have R1 almost equal to R2. So just like in a parallel plate capacitor where we had to have the plates as close as possible, here you need to have the spheres as close as possible. So R1 becomes almost equal to R2 and not as drawn in this diagram, really, really close. That's when the capacitance is higher. So that brings us to a cylindrical capacitor. As you can see, a cylindrical capacitor consists of two concentric cylinders of radii R1 and R2, and we assume that the lengths of the conductors are the same, So the outer one is given a charge minus Q, and the inner one accumulates a charge plus Q by electrostatic induction. So once again, applying Gauss's law, closed surface integral E dot dA is E times 2 pi RL is equal to Q by epsilon naught. Well, I forgot to mention, you got to consider a Gaussian surface like before. In this case, the Gaussian surface is a cylinder of radius little r, as you can see. The yellow outline cylinder is the Gaussian surface. The radius is little r and the length is L. So when we do the integration, once again, E is a constant taken out. So we have integral dA, and the surface area of a cylinder is 2 pi r, which is the circumference, times the length. So that's where you get this term. That is the surface area of that Gaussian surface. And now on rearranging and making E the subject, you get Q by 2 pi RL epsilon naught. Once again, voltage is the integral of R1 to R2 E dot dr. Substitute the value of E, and then when we integrate, we see that it's integral 1 by r dr, because all of these other quantities are constants, and integral 1 by r dr is natural log of r. So when we do that, you have Q by 2 pi epsilon naught times the length, natural log R2 by R1 when we substitute the limits. Finally, capacitance is the ratio of charge to voltage. So when you divide Q by the whole thing here, the Q's will get cancelled, and this entire thing flips. So we have 2 pi epsilon naught times the length divided by natural log R2 by R1 as the formula for the capacitance of a cylindrical capacitor. Now here is an important application of a capacitor that is used in tuning a radio. Okay, so here we have a set of fixed plates and another set of plates that can be rotated. So as you can see, the set of fixed plates, which is called the stator, and then you have this which can move in. So actually this one is the rotor, which can move in. And as you move them, the area that overlaps changes. As you move it more and more in, the overlapping area increases, and as you move it out, it decreases. When the area changes, we know that the capacitance changes. So this idea of a variable capacitor is used in tuning the radio. And this is called a gang condenser. Well, condenser is another word for capacitor. It just came out, okay? A gang condenser. When you look at the symbols of a capacitance, we know usually it's two parallel lines. That's the standard symbol for a capacitor. But sometimes you find this. That is a variable capacitor. So in fact, if you have an arrow over any electrical device, it means it's variable. That means its value can be changed. And if you see this, that means it's an electrolytic capacitor. Now, what's the difference? For normal capacitors, there is no polarity attached. So when you connect it into a circuit, you can connect either end to the positive or to the negative for standard capacitors. But when it comes to an electrolytic capacitor, you have to connect with the right polarity. And usually the shorter one is the positive and the longer one is the negative. That's also the code when you look at an electrical plug, an electrical receptacle. If you look at it, you see a smaller side, which is the live, and the bigger side is the neutral. That's kind of the standard. So if you find two leads on a capacitor, and one of them is smaller and the other one is bigger, then the smaller one is positive, the bigger one is negative. That's important when you connect electrolytic capacitors. All right, now let's look at what happens when capacitors are connected together. Often we got to combine capacitors, and the combination can basically be in series and in parallel. We'll talk about the practical applications of these as we go forward. But here is a combination of three capacitors connected in series to each other. All right. Now the important thing, and they are connected to a battery. As you can see, you see the negative plate, or the plate that gets a negative charge, is always connected to the negative of the battery. And the plate that gets a positive charge is connected to the positive. Also, you see that the opposite plate, the other plate has the opposite charge for sure. But what's interesting and very important is that no matter what the values of the capacitances are, when they are connected in series, they all have the same charge. The charges are the same. Very important. Same charge, but the voltages are different. So the voltage across each one will be different, but yet when you add the three voltages, it should add up to the total voltage of the source. So when capacitors are connected in series, the charges are the same, but the voltages are different. And the voltages add up to give you the voltage provided by the battery. So that's what is written here. Now it's a matter of simple substitution. We know that voltage is what? Charge by capacitance. So V1, which is the voltage here, is Q1 by C1, here is Q2 by C2, and so on. And then we are imagining that these three capacitors could be replaced by a single capacitor, as shown here. This is called the equivalent capacitance. We may call it the total capacitance, but it's the equivalent capacitance. And in that case, when it's connected to the same battery, it should have the same charge. That's where you get this. Now, mathematically, the Q's get cancelled, and we get 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So that is the formula to be used when capacitors are connected in series. Students usually make a mistake. Remember, it's 1 over C in series given by this formula. So after you do this mathematically, you got to take the reciprocal so that you get the value of the actual capacitance in series. Do not forget that. Now, if you connect it in... another thing I forgot to mention is that whenever you connected in series, the series capacitance is always smaller than the smallest amongst them. So if you had 1, 2, and 3, this would be less than 1, is what I'm trying to say. That's just a pointer to see if you're doing it correctly. Now, if you connect capacitors in parallel, then the voltages across them will be the same, but they will accumulate different charges. Now, look at this. Why is the voltage the same? If you look at how they are connected, you see that each capacitor is individually connected to the battery, as you can see. Each one is individually connected to the battery. Therefore, whatever is the voltage of the battery must be the voltage across the three capacitors. So that's the difference. The voltage will be the same, but now the charges will be different. And the total charge on an equivalent capacitance, shown this way here, a single capacitance, should be the sum of the individual charges. And Q is nothing but what? The product of capacitance and voltage. So when we use that and the voltage cancels out, we find that if capacitors are connected in parallel, the equivalent capacitance is simply the sum of the capacitances. That means the equivalent capacitance will be bigger than the biggest amongst them. Now, that's easy to understand. So if this is 1, 2, and 3 microfarad, of course, this is 6 microfarad, which is bigger than the biggest amongst them. Well, so that's something to understand. The important household applications of a capacitor is a stud finder that you see here. You're able to find out where exactly the stud is. And this is done by using the idea that when you have a different dielectric between the plates of a capacitor, its capacitance changes. So the stud finder basically has, as you can see here, capacitor plates. And as you move it along and as you reach the stud, between the plates now, instead of air, you have wood. And that changes the capacitance, and therefore that sends a signal, triggers a signal in the circuit, and you hear that beeping noise to show you that you've reached the stud. So we've already seen that the capacitance increases when you have a dielectric. And here is a table that lists dielectric constants. Notice that the dielectric constant is temperature dependent, so those are the values at 20 degrees Celsius. Vacuum, the dielectric constant is 1 because you compare the dielectric value with air. So air by air you get 1, air or vacuum is the same, you can see almost the same. And then paraffin 2.2, you come to mica, I told you it's 7. And look at that, water has 80. And this is a magnificent dielectric, strontium titanate, which has a dielectric constant of 300. So that will increase the capacitance 300 times. But another important constant is what's called the dielectric strength, given in volt per meter. It shows at what field strength the dielectric properties go away. That means the dielectric is no longer a dielectric or an insulator. It begins to conduct. It's interesting to note that air becomes a conductor when the voltage per meter is more than 3 times 10 to the 6. Well, we are safe, largely because the value is so high. When the voltage is 3 million volt per meter, air is a conductor. That's why you see sparks flying through. So when you see lightning, you know air is a conductor. That's because the voltage is now more than the dielectric strength of air. As you go down, you can see the different dielectric strengths, and that's where mica wins because it has a higher dielectric strength. Okay, so its dielectric properties remain until you reach that threshold of 150 million volt per meter. So we're going to now take a closer look at how the dielectric functions by looking at what is called dielectric polarization. All right, so you know there are 2 types of molecules, polar and nonpolar. So basically, the center of all the positive charges is at the center of the nucleus because the protons are positive, and that's where they are situated. And then you have all the electrons revolving in particular orbits, but they also have a center which normally coincides with the center of the positive charge. Okay, so the centers of the positive charge and the center of the negative charge coincides. So not only are the charges equal, they are also situated at the same spot. So there is perfect cancellation. Okay? But if such a molecule is kept in an electric field, as you can see on the right side, if it's kept in an electric field, so then what is going to happen is the centers move away a little bit in opposite directions because the positive center will move in the direction of the field and the negative center will move opposite to the direction of the field. So it's actually a molecular disturbance. It's so tiny, but it happens. And that's when we say the molecule is polarized. Okay, when the centers shift. So the shifting of the centers is called polarization. And that is shown here. See, the centers have shifted now. This is the applied field. So on the positive side, you see the center negative has moved to the positive side and positive has moved to the negative side. So that's what is shown there. And this is again called dielectric polarization. So we're going to see now when you have those parallel plates, and then if you put a piece of mica in between them, the molecules in the mica are going to be polarized. So they are all going to shift a little bit. Let me take you to this diagram and try to explain it from there. Okay. So when you look at this, here you do not have a dielectric. You only have two parallel plates, and this is the direction of the electric field, always from positive to negative. But then when you have a dielectric between them, notice what happened. The center of the positive of each molecule has shifted. See that? So the center of the positive has moved in the direction of the field, and the negative has moved opposite. Do you see that? So what happens is, inside the dielectric, it cancels out because this positive cancels out with the neighboring negative, and this positive with that other negative. But it leaves uncancelled charges on the outer surfaces. So here you would have a negative lined up, and you would have a positive, and there's nothing to cancel it. So that means that sets up a field which is exactly opposite to the applied field. Remember that the applied field was this way from left to right, but this field, as you can see here, because this side becomes positive, this side is negative, the field inside the dielectric is now opposite. So, this representation here shows that the field inside the dielectric has decreased. See that? Why? Because the applied field is, let's say, 20 units, and the field inside the dielectric is 7 units. So now, since they're opposite, the effective field inside is only 13, 20 minus 7. So the field is reduced. That means the voltage is reduced. When the voltage is reduced, remember C is Q by voltage. Voltage is in the denominator. When the voltage is reduced, the capacitance goes up. So the ability of this capacitor to store charges has gone up. All right, that's once again the same diagram is shown here, as you can see. First, before you had the dielectric placed, you have lines closer. You see that? You know that the density of the lines shows the strength of the field, right? But here the lines are further away, showing that the electric field has come down. So very important to understand. So when you situate a dielectric between the plates, the electric field goes down. That means the voltage there goes down, which means the capacitance goes up. And that is why the formula now becomes K epsilon naught A by D, where K is the dielectric constant, which is just a number showing how many times the permittivity is bigger than that of air. Okay, this is the permittivity of air. So if it's mica, it's going to be 7 times the permittivity of air. So that is what it shows. Finally, let's find out the energy stored in a capacitor. So, wow, that moved so fast. How do you define energy? Energy is always the work done. For example, the potential energy of an object is the work done in lifting it from the ground to a certain height. So when you talk about the energy of a capacitor, we're going to consider that this capacitor is starting out from zero charge, just like that object was on the ground. So it's starting out with zero charge, and slowly but surely we are adding charges to the capacitor. That's usually done by connecting it to a battery. But for theory, we're just imagining it's added in chunks. So the small work required to add an additional charge dq is given by V dq. Now that comes from the definition of voltage. Remember that voltage is work over charge. Voltage is work over charge. So when you rearrange, work is voltage times charge. So integral V dq gives the small amount of work that you need to do. In fact, it gives you the total, because when you integrate, it gives you the total work. And then we substitute for the voltage as Q by C, where Q is the charge already on the capacitor plates. And then we wanted to add an additional dq. Okay, so Q by C is what voltage is. And then you know C is a constant, so it's taken out, and then you integrate Q dq, and Q dq is Q squared by 2. And then the limits of integration are from 0 to a maximum charge caps Q. So that gives you Q squared by 2C, as you can see, because integral Q dq is Q squared by 2. It gives you Q squared by 2C. And that is the potential energy of a capacitor, U sub C. U always signals potential energy. So this is electrical potential energy of a capacitor is Q squared by 2C. But we can get two other formulas by simply substituting. We know charge is capacitance times voltage. And then when you substitute that, you're going to get this. You're going to write as CV squared. So one of the capacitance will cancel out, and you will get 1/2 C voltage squared. Or it's another one, by similar substitution, you could get 1/2 times charge times voltage. So there are three formulas to find the energy of a charged capacitor. Okay, we've gone through this very important chapter. Remember that this chapter began with the primary ideas of electrostatics, where then we went to electric field, then we defined electric potential, then we had Gauss's law, and finally we came to a capacitor. So these 4 chapters actually is a series of chapters that culminates in one practical application, very important one at that, a capacitance, a capacitor. So I hope you study these 4 chapters as one piece, as one section. And I hope you really understand that a capacitance is an electronic piece that's so important and that has several applications. All right, make sure you work out the problems in this chapter like in every other chapter, and see you in the next chapter. Thank you.